Okay. All right, we're on to lesson 4 here. We're getting to the point, right? So just doing this warm-up real quick. Name the geometric solid associated with each situation. A stack of 100 copies of the same book. So they're all congruent. Assuming the book is a rectangle, then we have a rectangular prism. Stack of 100 tires, all with the same radius. Assuming that the tires are circular, which they I guess always are, we would just think of them as a cylinder, right? And a stack of 100 stop signs. Well, a stop sign has 8 sides, right? So it's an octagon. So a stack of 100 stop signs would be an octagonal prism. Octagonal prism. So again, the prisms are defined by the shape of their base. Like we call this a rectangular prism, but if it has 8 sides, it'd be an octagonal prism. Describe a stack of objects best represents each geometric solid. So this would be like a stack of pizzas would be a cylinder, right? A stack of, maybe square stamps. If you stack them high enough, they'd be a cube. And a triangular prism would be like a stack of, what's something shaped like a triangle? I don't know, maybe one of those flags you see on a ship, or a pennant, right? A pennant is a triangle, usually. So a pennant is like a long banner that is usually in the shape of a triangle. So a stack of pennants. Okay. Given formal arguments to explain the volume formulas of pyramids and cone, we're going to explain the area and volume formulas using Capillaries Principles again. And we're going to use the formulas for the volume of a cylinder, cone, and sphere to solve real-world problems. So here we go. Lateral surface area. The lateral surface area is the area on the side, right, of a lateral face. So that would be lateral surface area. Total surface area would be the surface area, what it would take to cover the lateral faces and also the bases, top and bottom, right? And just think of it as like, how much paper would it take to wrap a box in, or how much paint would it take to paint the outside of a prism or a cube or whatever. And we're going to get into spheres. Spheres are those shapes that we did yesterday when we rotated the disc, a circle on a pencil, and it forms a sphere. We're talking about the radius of a sphere, the diameter of a sphere, a great circle, and a hemisphere. Okay. All right. So today we're going to be working on, the volumes of formulas for prisms, but how would we figure out the formulas for the volumes of pyramids and cones? So now imagine when we stacked pancakes on top of each other. Remember how we said, like, who's good at making perfect circular pancakes? I know I'm not, right? So instead of making perfect circular pancakes, let's imagine that we have them and they keep getting smaller. We make a big one and then we think that's a little too big. Let's make it a little bit smaller. And we just keep doing that. We keep making it a little bit smaller and a little bit smaller. So it's going to look something like this. Here's our first pancake right here. And our next pancake sits on top of it right here like this. Then our next pancake sits on top of that, kind of like this, and like this. And what are we doing eventually with all these pancakes? Well, they're going to get to a point, literally, where, since they're getting smaller and smaller, they become so small eventually that you can't even see anything beyond a point. And now let's consider this overall shape, right? The overall shape, is, oh boy, sorry. Let's get the line here. The overall shape is a line down as these get smaller and smaller, right? And a circle for a base. And in case you haven't already guessed it, this is a cone, right? Just a bunch of discs that are circles that are similar. All right, they're not congruent. They are similar. And each one is slightly smaller than the last. And so, when it says identify the name of the solid formed, we're going to put in, oops, I forgot to edit, hit the edit button. So now we're going to put in the name, and the name is going to be click that off to the side. It is going to be a cone. Okay. relate the dimensions of a single pancake to the dimensions of the solid. So a single pancake has dimensions measured by the radius in 2 dimensions, and it would have a height as well. The cone has the same 2 dimensions with each slice getting smaller in each what we call cross section of the cone, as well as a height. Okay, we'll just put it that way. Imagine you stack similar square pancakes on top of each other so that each layer of the stack is composed of a slightly smaller pancake than the previous layer. So let's draw that one out too. So here we go. I've got a square pancake. You know what? Let me start that again. I'm going to draw it like, even though this is a square, sorry, let's try that one more time. So even though this is a square, I'm going to draw it on a diagonal so we can just see. Imagine that this square pancake is sitting on the counter. It's actually a square, but you know, just because of how it looks to us and the angle that we're looking at it. So if I kept stacking similar but smaller pancakes on top of it, what shape would that eventually take? So imagine I keep getting a little bit smaller and smaller and smaller. And what am I going to end up with? Maybe put another one in between here. Actually, you might recognize this shape if you've ever seen pictures of the pyramids, right? Because this is going to take the shape of a pyramid. Okay? So it goes up, 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 up to a point. Okay? So there's different types of pyramids. The pyramids all start with some kind of a polygon for the base, and they rise up with similar polygons all the way up to a point. Okay? And that is a pyramid. So let's add in a little text here. Here we go. The shape would be a square pyramid. Okay, the dimensions of a single pancake. So a single pancake would be, you know, in the form of a square. So we could say length and width that are equal, and some height, not much. If it's a pancake, it's going to be, you know, fairly thin. And so what do we have? We have length and width that are not equal to the base, but gradually reducing. And then there is a height as well, right? It's going to be non-trivial height. It's some height that, you know, depending how tall we stack it. Okay, imagine you stack similar triangular pancakes. So what would be the name of that? Doing the same exact thing. So this would be a triangular pyramid. Okay, dimensions would be the same. So in a triangle, the sides of the triangle, right, that would keep getting smaller if we go up, and then there is a height factor, right? All right, so what do you notice about the three-dimensional solids created by stacking similar figures? Well, I noticed they, form either a pyramid or a cone depending on the shape of the base, right? What type of solid is formed by stacking similar rectangles? Well, similar rectangles stack to a rectangular pyramid. Pentagons would stack to a what we call a pentagonal pyramid. And hexagons would stack to a hexagonal pyramid. Okay? This is what we're doing with all of those names of the different polygons, is that we're taking, once we get past the rectangle, okay, we get to the pentagon, and so it's pentagonal, hexagon, hexagonal, etc. Right? We did this before. We said octagon was octagonal, right? So you would just take the name of the polygon and add AL to the end of it, and pyramid. I put an N in there. Okay, that's how that works. Okay, so now it says, think about how we can derive the formula. Here we have some pyramids here. Here we have a pyramid right here, right? It has 4 spaces and then 1, or 2 across and 1. So 1, 2, 3 is, if you measure the dimensions, right? You have 1 centimeter cube, 2 centimeter cubes, 3 centimeter cubes. So describe the two-dimensional shape of the top surface of each layer of cubes. So the top surface of this cube is a square, right? And each layer has another square. So this one has a little square that's 1 centimeter by 1 centimeter. This next layer has a top surface which is a square 2 by 2, and then another square here 3 by 3. So describe the two-dimensional shape of the top surface. It is a square, first 1 by 1, then 2 by 2, and finally 3 by 3. Explain why the two-dimensional surfaces of the cube layers represent similar figures. Oh yeah, they're all squares, right? So they are all squares. So they have similar properties, or they have the properties of similarity. They have properties of similarity and can be created by using a dilation, which is a similar transformation, right? All right, what is the volume of each pyramid? Well, we can count this one. This one is 1, and then there's 4, so it's a total of 5. So the first has a volume of 5 cubic centimeters. The second one has 3 by 3, that's 9, plus 4, 2 by 2, that's 4. So 9 and 4 is 13, and this is 14. So the first has 5 cubic centimeters. The second has, 14 cubic centimeters. All right. For each of the two pyramids, determine the volume of a prism that has the same base. So what would we do? The volume of a prism that has the same base. How would we figure that out? For each of the two pyramids, determine the volume of a prism that has the same base. Well, when we figure out what this area was, right, and then we would multiply by the height if we were stacking them, right? So if they had the same base, and then we were just stacking on top of them, the volumes would be the same, right? If we went up, but we started with the same base, the volumes would be the same, right? Now, the volumes of a prism. Sorry. I'm so sorry. This is asking us for the volume of a prism. So the volume of a prism for the first pyramid would be, so if we look at that close, we have a area down, or volume down here of 4 cubic centimeters. If we add it on top, it would be 8 cubic centimeters. So it would be 8 cubic centimeters. The volume, of the second prism would be, alright, so if we take a look at the second one, so we would have 9 in that first row, and then the second row would also have 9, and the third would also have 9. So it would be 27. It would be 27 cubic centimeters. Okay, use centimeter cubes to build a pyramid with each number of layers. Oh boy, they want us to do that, and we're not going to do it with centimeter cubes. So we're just going to fill this in. If it had 1 layer, it would be 1 cubic centimeter. If it had 2 layers, well then it would be 4 on the base plus the 1, so it would be 5. If it had 3 layers, we did that. That was 9 plus the 4 is 13 plus the 1 is 14. And then down here we would have 4 by 4 is 16, and then we would add in the other 14, and we'd end up with 30. Okay, so what is the volume of the prism with the same base? So if I had a prism with that would be 1, right? Okay, and if I had a prism with a base of 4, this would be 8. If I had a prism with a base of 9, and 9 units up would be, let's see, I'm sorry, 3 units up, that would be 27. And then if I had 4, right, and I went up 4 units, so 16 times 4, that'd be 64. Now they want us to put the volume of the pyramid over the volume of the prism. So in this case, it would be 1 over 1, right? And here we have 5 over 8. And here we have 14 over 27. It's getting smaller. You see that ratio? And 30 over 64. Oops, I put 20, but it should be 30 over 64. So this is 1, right? This is 0.625, something like this. This is a little less than, or a little more than half, just barely over 0.5. You do that math yourself and figure it out. This one here, 30 over 64 is just under half. Okay, it says, how does the ratio volume of pyramid to volume of prism change as more layers are built onto each pyramid? And so what happens is the pyramid the ratio is getting smaller, right? It's getting smaller. Okay, so the ratio is getting smaller. I'm not sure if that's what's supposed to be happening here. I wonder if I'm answering this question the way they mean for me to answer it. So let's just check again. The volume of a prism with the same base, if it had 1 layer and one let me just think about this. You know what? I think we're going to redo this a little bit. So let's try this again. Let's imagine that there were, in that 1 layer, that there were 9 total total cubes, right? So let's go back and look. So it's like this if we just had 9 total cubes in 1 layer, right? So let's try this again because I think we're looking for a different answer here. So if this was 9, there would be 9 in the pyramid. I don't know if that's what they really want me to do either, but we'd say 9 there. Now if I had 2 layers and it was a pyramid, yeah, no, that has to be it. Anyway, here's the point. It says if you keep going, build a spreadsheet to extend your exploration. In the first row of a spreadsheet, enter the column headings. How good are you guys at spreadsheets? Spreadsheets are really, really powerful tools. So let me see if I can get a spreadsheet up over here. So we'll go Sheets. And just make sure you see how this works. We're going to try and do this here. Okay, I'll just get a new blank spreadsheet going here. And they want us to, well, it's loading real quick. We're going to, in the first row, enter the column headings. So we're going to put in number of layers, number of pyramid, or volume of the pyramid, and then the volume of the prism. So let's go with number of layers, and then the volume of the pyramid, and then the volume of the prism, and then the ratio of pyramid to prism. Okay, and so I would start here and go 1, 2, 3, 4, 5, 6, 7. Okay, and what's nice about this is, let's just highlight all that and we'll just drag it down here somewhere. Okay, and now the volume of the pyramid. So the volume of the pyramid is equal to, there's 1 plus, the next row would have 2 squared. So it's equal to this number squared, right? So that gives me 1. And then this is equal to this number squared plus that number. Okay? And then we're going to use that same formula. Okay? So we get the 14, 30, 55, 91. And this is just adding 25 to the 30, 36 to that. So you see how I wrote that? I take the number on the left, the layer that we're on, square it, and add it to the previous, right? So the number, the volume of the prism is now equal to this squared times the height, right? So it's actually cubed. So this would be equal to this to the 3rd power, right? If I had a prism, and then the ratio would be equal to this number divided by that number. And that's my ratio. Pyramid divided by the prism. Okay, so this number, this is good. I see what they're wanting us to do, and I think it's great. In fact, I'm going to scroll down some more, and we'll do it maybe a lot more. This is what they're asking us to do. The ratio is getting smaller, and now they want us to do that. And then let's see, what do they want us to do? They want us to go pretty far, I bet. I bet we can go a long way. Okay, it says go 10 rows, but I'm going to go, it says extend your table to at least 100 rows. Okay, so here we go. We got this down here, and I'm going to scroll down to, 100 or so rows. Here we go. This is just counting up. All right, we're up there a whole ton. Okay, and now we're going to go this way, right? Take these oops, I don't want that first formula. I don't want that formula. I just take this formula down all the way 100 and whatever that is, 17 rows. Okay, and we'll take this formula all the way down. Okay, and then we'll take this formula all the way down. Yeah, I see what they're doing here. They're wanting us to really see what happens. And it is an interesting thought, okay, that we're going to kind of come to. What do you notice that's going on? So it started out way up here at 1, right, this ratio. And it kept getting smaller and smaller. And you might be tempted to think, oh, it's going to go down to 0. Well, it's never going to get to 0 because the volume of the pyramid is never going to become 0. But what you notice is as the number is going down, first goes down a lot, right? And that's because you have one big square, and then, the volume of that 1 cubic pyramid is the same. It's the same exact object, right? But as the object gets smoother, you think about making more and more layers in your object, then the numbers here start to change less. I don't know if you can see this, so I'm going to try to zoom this in some more. But you see here you have 1, and then it goes to 0.625, right? But then pretty soon, it doesn't take long. We're only at 10, and we're already in the 30s here, 0.385. By the time we get to 20, we're down to 0.35. At 30, we're still 0.35. So it hasn't even changed that much, you know. Less than a hundredth of a percent, right? Or actually, less than 100th, so less than 1%. The ratio is dropping very slowly now as we get into the 70, 80, 90, and we're getting really close to 0.33, and we got 0.3376. And if we continued indefinitely this ratio, guess what it would work out to be? It'd be 0.3333333333. That's what it would work out to be. Maybe we'll even do that. I wonder if I just go down here, like, since it's a spreadsheet, you kind of just have that advantage that you can just go a long ways and really just let the thing do the work for you. Maybe I won't go too far, though, because my computer will get locked up. I don't want to do that. So I'll bring it here to 507 rows, and then we'll take this formula that we have up here and just go down to 507 rows too with it. Grabbing that corner, dragging it down, just brings down the formula. Oh, wait, what am I doing? You know what I can do? Be smart about this, right? I just want to continue all 3 of these formulas, so I will grab all 3 and bring it down to 507. And then let the computer do a little work on that, figuring it out. But it's going to be approaching 0.333333. And this is just not proof of anything. This is an observation we're doing here, you know, so you could form your own conjecture, right? And you can see it's getting closer to 0.33. We're at 0.334. If we kept going to get closer and closer. And if you think about a pyramid with 500 rows, though that doesn't look so less like a pyramid. Now let's go back to that image real quick. You know, this right here with just 2, that doesn't even hardly look like a pyramid. 1 wouldn't even look like a pyramid. Right? 2 rows is a little bit. 3 is looking a little more. But, you know, if I were to make this into a ton of rows, right, that were each one consecutively just a teeny bit smaller than the last, well, then that shape of the pyramid would it would start to appear smooth, right? 500 rows of these blocks going out, it just start to really look like a pyramid, okay? So we did the exploration here with that, and we see that as the size of the pyramid increases, I would say it approaches 0.33, you know, etc. And is there a limit to this ratio? You know, it would appear so, right? It cannot get to 0, right? It cannot get to 0 because there will never be a 0 in the numerator. That's the number on top of the fraction. There will always be some volume in the pyramid. It cannot reach 0. So there has to be a limit, right? Someplace that it approaches. So what generalization can you make about the relationship between the volume of a pyramid, okay, with the same base of height? So this is where this number becomes very interesting. 0.333 repeat forever. So what does that represent? 0.33333 repeat forever. So the generalization I can make, is that the ratio will be 1/3, 1/3. So now what would be the formula? Well, the formula would be, I would just want 1/3 of, that star means multiply, right? And when we say these words, 1/3 of, almost always we use times for of, right? So 1/3 of the area of the base, right, times the height of the pyramid. So another way to put that is 1/3 times the area of the base is side times side. So I'm going to put that side squared times the height. Okay, that is the formula for the volume of a pyramid with a square base. Okay, would it apply to pyramids with non-square bases? And we'd say, yes, the area would, the volume would still be 1/3 times the area of the base times the height. Okay, Denny says that an oblique pyramid like the one shown doesn't have the same volume formula as a pyramid that is not oblique. So they gave him a thumbs down for saying that, Denny. Maureen disagrees. She says that the same formula works for both. Who is correct? Explain why. Well, remember, as long as we're not using slant height here, then the volume, if you think about what Capillaries said, who cares once you've calculated the volume if you tip the slices towards one side or another, right? So, so the answer I would say is that Denny is correct. I'm sorry, that Maureen is correct. The same volume formula works for both. And the only thing that has to happen is that we're going to make sure we use the right dimensions here. We need height for it. Okay? You think the formula derived applies to pyramids with non-square bases? Explain your reasoning. Okay, so if it has a non-square base, we could still find the area of the base and use our formula. Right, we just substitute out the area of the base. Okay, it says building the cone volume formula. So thinking about cones and pyramids, right? If you were to slice them, right? If you were to slice them across, remember that every slice that we made would end up in a figure that is similar to the base. The figure in the cross section here is similar to the base. It is just smaller, right? Capillaries Principle states that if a plane cross section parallel to the given plane has the same area in both solids, then the volumes of the solids are equal. And here it says the bases have equal area. So if the bases have the same area and the cross sections have the same area, then what would Capillaries tell us? He would tell us if the heights are the same and the cross section of every single slice has the same area, that the volumes would be the same. Okay, if the length of the radius of the base of the cone is r, what is the area of its base? It would be pi times r squared, right? The side length of the base of the square pyramid is s. What is the area of its base? It would be s squared. You're given that the areas of the bases are equal, so set the areas equal to each other. Rewrite the equation in terms of the side length of the base of the square pyramid. So side squared is equal to pi times r, and then that would be squared, right? And so now rewrite it. So I would take the square root of both sides, and I would say s is equal to, oh, wait a minute. They want us to rewrite it in terms of the side length of the base. So we're basically going to solve for r, I think is what we're doing here. So we'd say r would be r squared. So r squared is equal to pi, put this in parentheses, s squared over pi, because we divide both sides by pi, and then we take the square root of it. R is equal to the the square root of, and then we're going to have s squared divided by pi. Okay, so we take the square root of that whole thing right there, and I'm going to just drag that out a little bit. Okay, so now we still have r in here. We know what r is equal to, so I think they're wanting us to go back and substitute this in for r, and then we would be able to just have the equation with S only. I'm not going to do it. We're going to skip that, and it's okay. Let's take a look here at this next part. It says it's just too hard. It's not hard to do this maybe on a board or something, but it's hard to type that math out. And I don't want to lose you guys just going through some algebraic exercise there. It says you can use similar triangles to show that the area of the cross sections are equal. So here they have the equation for the length of the radius of the cross section. Okay, and we're going to skip through this algebra right here, right now, because for the purposes of time. So the area, this is an okay probably exercise, but I just know with our class I'll lose you if I spend a whole lot of time digging into that, and I don't want to do it. So it says, use Capillaries Principle to explain how the worked example shows that the volume of the cone equals the volume of the square pyramid. So here what we're basically going to say that we would use this, we know what Cavalieri would say. He would say if the area of every cross section of that is parallel to the base in both cases is equal and the height is equal, then the volumes are equal. That's what Cavalieri would say. And then this is, I guess, an algebraic proof of that, which we're not going to do. All right, and it says, explain how you know that the formula for the volume of a cone is 1/3 times capital B. Notice this capital B, and that capital B means the area of the base times the height. All right, well, in essence, one thing to just know is that you think about cutting away, right? We'd be cutting away in 2 dimensions, right? We're reducing in 2 dimensions the area, right? So that leaves only 1 dimension that's there. So as the base gets smaller in 2 dimensions, as we're reducing in 2 dimensions, but we're continuing the 3rd dimension, then we are left with 1/3 of it. And I think that's simple enough to kind of follow, and it's enough definitely for what we have to do in terms of being prepared for our tests and getting through the grade that you need. Okay, let's investigate the volume of 2 different cylinders created with a standard size sheet of paper. So if you take this is a good little exercise. Let me draw this out, right? So let's just see if I can do this here. So we're going to start with a, excuse me, we're going to start with a sheet of paper. So here we go. We've got it is maybe long on the one side, 11 inches, and then it's going to be 8.5 inches, and then 11 inches and 8.5. So you see something like that. Now, how can we roll this up? We can roll this up like this into a big circle that then would look, let me see if I can sketch this out. So it would kind of go around like this, right? So that if this is 11, right, and this is 8.5, this measures 8.5, right? So then the circumference of my cylinder would be 11. The circumference would be 11, and then the height of the cylinder would be 8.5, okay? Now, if we rolled it the other way, so that we rolled it, let me get a different color here and see if I can do this. So, in other words, instead of rolling it this way, we're now going to take this edge and we're going to wrap it around that edge until they roll around. Then we end up with a thinner 8.5 inch circumference, 8.5 inch circumference, and taller cylinder, okay? And this would be 11 inches tall. So now they want to know which cylinder has the greatest volume. So we would have to calculate the volume. So how would we do that? Well, remember this radius is unknown and this radius is unknown. But we know the circumference here is 11, right? So we can use our formula to calculate the circumference, or to calculate the radius, and we say 2 pi r equals 11 and solve for r. Now I'm going to let you do this on your calculator yourself. So let me take this off, and I'm just going to type out what you'll need to put into your calculator, right? So pretty much what you're going to need to do is you're going to say, okay, 2 times pi times r equals 11, and then you would solve that one for r. So we're going to put solve over here in the front. Right? And then once you have r, you're going to go pi times r squared to get the area of the base, and then you're going to multiply that by the height. So you would do that, and then you would do it again. Solve 2 times pi, oh, the height was 8.5, sorry, 8.5, right? And then down here you're going to go 2 times pi times r equals 8.5, and you're going to solve that for r, and then you would do pi times r squared, and then times the height of 11. Okay, so after you find r the next time, plug it in here and find out what it is. So now, which cylinder has the greatest volume? So just thinking about this, you know, the difference between 11 and 8.5, I don't know for sure, but when I'm squaring the radius, that is going to have the best, I think the largest impact on increasing the volume, right? Increasing this factor of height is one thing, but increasing the radius by the square of the difference seems to me like this one would probably be more. But that would be my prediction, and I'd have you go ahead and do that, okay, and calculate that and prove whether or not it's correct. Okay, surface area. We're going to do this surface area thing, and then that's looking at the time, all the time that we have today. So lateral surface area. So here's where we have a right cylinder. Okay, the bases and the lateral faces. So the bases are the two circles. The lateral faces of the circle. And actually, as I look at this, I'm realizing you are actually out of time right now anyway. Because we are through, I forgot that we had 2 other videos that you'd already watched today. But if you have a little more time, you can go ahead and work through some of this on your own. And I will, as soon as I can, be back in classroom to help you guys work through the rest of this stuff and get ready for your test.